Okay.
I think we'll have to invent something like elevator music. When people are fiddling with their communication systems, then they turn it on right away. Some music. Oh, nice.
I've just been admiring your beard, Sanjeev.
Oh, oh, believe me, I think for about 3 weeks, 4 weeks, for a full month, people were just talking about the beard. Now I think at least in the department it has become old talk, but it is still. I
Okay.
think I'm waiting to see my mother's reaction. But anyway, sorry, Andrew, yours.
Not a problem. Hopefully you can all see the screen here. Um,
Yes, Ken.
s- so
Yeah.
I'm gonna go over kind of a high level overview, echoing a lot of what Sanjeev just mentioned, and more specifically describing how it's going to be implemented in a course that has applications in both a first year environment, an upper year environment, as well as a graduate level environment. So really what that means for the audience that's on the teleconference today is kind of their level of comfort with the governing equations surrounding what's going in the analysis engine of whatever analysis they're performing using the Ansys suite of software, as well as how much experience level they have with finite element modeling in general and digital twins and things like that. So kind of a problem statement that we've came up with, and it's an overall objective, is just to understand the multifaceted approach towards product development from an engineering perspective. And we use the term product kind of loosely because we describe as Sanjeev mentioned, a machine that we're using a very simple machine as an example of a generic product development. So this will be kind of accomplished by providing the students a platform where they can understand and apply all the engineering concepts that they're learning in their classes. However, they're going to get these concepts reinforced by conducting a collaborative IoT enabled experiment of a life cycle test of a simple machine. So we've chosen a chair to be the simple machine, but I will explain why in a little bit. So they'll analyze the data that they collect from this test from a multitude of different sensors. They'll create an analysis model to draw insightful conclusions, and then they'll have a predictive life model that incorporates a whole bunch of sensor fusion and what we call experiment in the loop. So moving towards the objectives and goals, I'll just kind of breeze through this slide quickly, but they're going to effectively develop an understanding of the type of data-driven decision making that's required to conduct a scientific experiment. So that's depending on the student's level of background. They might have a lot of detail-oriented experience in that, or they might be totally new to that idea. Um, one thing that the analysis will help us to do a lot is interpret and analyze results in real time. Via an IoT enabled machine. So on the experimental side of it, we can freeze frame effectively what's happening in the experiment to look at the predictive part of the equation. And then in the experiment, we can look at the time histories of what's occurring and get a different sense of what the data is doing. Obviously, they'll have an exposure to a variety of different experimental techniques, so that's good, and with a variety of different sensor inputs. So understanding things like accelerometers and strain gauges and force gauges and pressures and temperatures and things like that. And finally, we want to incorporate AI, artificial intelligence, to optimize the way that the machine is operating, the way that our analysis model is optimizing the result, and the way that we're interpreting the results to automate the procedure a little bit, with the objective of improving reliability, manufacturability, sustainability, or cost. So that's kind of the overreaching high-level overview of what this project entails. Kind of a step-by-step process flow of what's going to happen is it really stems in product failure. So we selected a simple IKEA chair. This particular chair has two cantilevered legs. So instead of having a typical four-legged chair, this is a much cooler scenario from a simulation point of view because first of all, it's not an indeterminate problem, and there's visible displacements, which is really cool because you can visually see what the chair is doing under load. Kind of the more pragmatic objective is that many of the students have these. If you live in a dorm room or if you're a student in general, you have exposure to this chair and you sat in one in your personal life. So investigating kind of a typical product failure. I have an example of one of the chairs that I've actually had in the past year. I was able to take a picture of kind of where it sustained some fracture after many years of use and potentially abuse. Um, the things that we're trying to teach them is how effectively does the design of the chair itself, the materials that go into the chair, and as well as the manufacturing methods that are used to create the components that compose the chair, how those three elements can relate to something that you see below here, like a durability issue, and what implications does this have on, say, the warranty of a chair or the cost structure of how the company actually decides to sell it. So this is kind of a multifaceted approach towards product development because it's taking into account all of these different financial, structural, and let's say environmental issues that would go into developing this type of product. So the second thing is usage data. Hopefully, let me see if I can move this over here. So usage data, we would effectively instrument the chair with a variety of different sensors and allow a variety of different people to sit on it in a different loading environment. So it could be children, it could be adults, it could be people that are placing their bookcase or sorry their briefcase on it. It's people that allow their pets to sit on it. We might put these in a few different locations throughout the university and just collect in say lobby type environments where the chair is just open for public use, and effectively we're going to get usage data and the frequency spectrum of how the chair is getting used and types of load cases that are kind of driving the usage cases. So is it a large number of people that are sitting on it, or is it a large number of objects that people are just resting on it? Are people sitting asymmetrically? Are they leaning back in the chair? Those types of things. So depending on how we instrument it, it will allow us to collect data to kind of support any of those different usage statistics. The reason this is being collected is because effectively we want to understand, well, why did the chair break in the first place? So we want to see which load cases are really happening to a chair in typical usage, so then we can actually model it. So step three would be to, excuse me, my computer is a little bit slow right now. Right here, create a digital twin via a finite element model. So what we can do is have the structure modeled in CAD. As many of you are familiar with, we can apply boundary conditions and material properties, loading, and effectively enable some different parts of the analysis engine to either see different levels of detail, which what we want. We could have nonlinear geometry, nonlinear material properties, or we could just do a simple stiffness type load case, or we're just investigating, well, how stiff is the chair and how much does it move under a reasonable load case. And the reason that this is important is because we want this digital twin to understand the discrepancy between the experimental data that we're collecting in step two and eventually the simulated data that we're going to generate when we simulate the final load cases that we're concerned with. So what's happening here is we're going to correlate effectively this digital twin. So the analysis result that we're getting, we're going to correlate it to the usage data. Okay, we're inputting things like material properties, Young's modulus, bulk modulus, material strengths. We could have a nonlinear material curve. But if any of you have sat on this chair and maybe you can see from this particular image, I'm not sure what material this chair was made of. The picture was taken several years ago, but the latest chairs actually have bamboo arms. So if you know anything about wood and fibrous material, there's a grain structure in the wood and it has different material properties in different directions. Modeling that is quite difficult. Also, where you get the wood from, if you get the wood from Japan or you get the wood from Southeast Asia, it'll have a different density, a different modulus, and all the material properties effectively differ. So this is an exercise also in teaching the students in the variability in the inputs that you're giving them. It also has a direct correlation to the results that you're getting. So how can we see what we're seeing or the results that we're seeing in the analysis prediction? How can we correlate that back to what we're observing in the usage data? And then we'll iterate, and this will create a loop that will effectively allow us to calibrate and validate the FEM for that particular load case. And we could do the variety of load cases that we're investigating in this reverse engineering phase of the load case. So hopefully that makes some sense. Then we can move forward to step four, which is once we have a validated finite element model, we want to separate the damaging and non-damaging load cases. Okay, so we'll create or we'll collect some usage data in terms of forces, displacements, We're even using things like acoustic signals to extract actual load cases from. So depending on the frequency spectrum of the acoustic signal and the amplitude of the signal itself, we can determine what type of load case it is and effectively how much the magnitude of the load case is. So we're using a variety of different sensor inputs to effectively record what's happening. But this is a simple case of just measuring forces, let's say, and we can see that there might be a peak and a valley here, and those low cases would be deemed significant. And then there might be some oscillation occurring after we sit on the chair, and those are non-damaging because the actual amplitude is a lot less. Okay, so that's important because when we collect the usage data, we're going to have a ton of time history data to sort through. And an important part of what we're trying to teach the students is how can we effectively filter that data to extract the meaningful parts from it that are actually going to drive the design and remove all of the content which is not significant or non-damaging. So once we have that, we are going to develop a test apparatus. So effectively, we're going to have a whole bunch of load cases that we're going to be extracting from the data that we're collecting in step 2, which is the reverse load case engineering or the reverse engineering of the load cases. And then we're going to say, okay, well, we have 4 different load cases that we want to investigate. One where the person sits on the chair right in the middle of the seat, one where they equally distribute their weight from the seat to the back, one where they're asymmetrically sitting on the chair, let's say, and one where they're, let's say, abusing the chair and they're leaning back really far. That might be just an example of 4 load cases that we want to simulate. But from that, we can see that we need 2 load actuators to actually mimic those types of things in a test apparatus. Okay, so instead of using people to collect the data, now we are going to develop a test apparatus that has load actuators that can accelerate the data collection or effectively the load cases that we're exhibiting the chair to so that we can accelerate the fatigue damage and get a result a lot quicker. Step 2 might take, I don't know, 2 to 3 months, let's say, of collecting data before we get enough to be representative of kind of the statistics of what it means to sit in a chair. Then what we're going to move forward from there, once we have developed this test apparatus, we'll actually conduct the durability testing with the same suite of sensors that we used in the reverse engineering of the load cases. And we're going to effectively test the chair to a few different thresholds. It could be one, whatever we deem to be one fatigue life. It could be some factor of safety on top of that, or we could just test it to failure. It might last 10 fatigue lives or whatever. But that particular margin of error that we're getting is directly correlated to, well, how much factor of safety is there in the chair, and are we using more material than we really need in certain locations, and can we improve the performance of the chair, or can we reduce the cost, or can we improve the manufacturability or something like that. So the failure location that we're observing here in the actual durability test, we want to correlate that to the Ansys model here. Okay, so all of the inputs that go into the Ansys model, such as the boundary conditions, the mesh, the material properties, what elastoplastic model we're choosing to use, the fatigue properties, the damage model that we're using to assess the fatigue damage, and then we're going to refine that into kind of a holistic model that we're going to call this Ansys model to improve the fidelity. So we're going to use the test data to improve um, the Ansys model or the predictive model or the digital twin, the result from that. And this is another iteration loop to do the finalized correlation, because now we're correlating it to not the actual test data. It's going to be the accelerated durability test. Okay. And the overreaching goal is step 9 here, which is accelerated design. Once we have that step complete, what we can really do is remove the chair itself and drop in an entirely different machine. Okay. And this whole process, the framework of this process will remain the same, but we're just changing the load cases, let's say. Even more simply, we might say, okay, well, what if we have a different load case now, where instead of we're not designing a chair, we're designing a bench. Okay, and the bench might have asymmetric loading. It might have a more severe load case. Or we're worried about, let's say, what if we want to dampen these oscillations here? Okay, because someone might spill their beverage that they're holding in their hand if the chair oscillates when they sit in the chair. Okay, so instead of approaching this from a structural perspective, that we want to minimize the stresses and the strains in the parts of the design that might fail, we might want to increase the stiffness of the chair so that it doesn't oscillate as much. So depending on that, once the students understand this framework, we can actually sell them a whole bunch of different product design environments that will allow them to understand kind of product design in general. Um, yeah, so that's kind of the overreaching process flow of what's going to happen, and we have conducted some preliminary testing to fulfill a few of these different steps of this process. So I'll jump to that now. So I actually do have one of these chairs at home. During lockdown, it was difficult to go to IKEA, so I was lucky enough that I had one of these at home. And what we did is we wanted to kind of um, use a very simplistic method to extract the type of data that we would use for that correlation step in the reverse engineering of the load cases. So what we did was implement three LEDs on the chair itself. You can kind of see them here. I'm not sure if it's showing up on your screen very well. When I bring up the video, you'll be able to see this quite easily, hopefully, where there's a yellow, sorry, this is just a still image, but there's a yellow, a red, and a green LED here that you're looking at. And they're located at specific hard points in this CAD model so that I can accurately, or we can accurately measure distances and calculate displacements from these particular lights. Okay. Then using an optical technique, what we did was digitize the motion of these LEDs as I sat down on the chair. So this is just a typical load case sitting down in a very controlled method. We're using a software suite that actually looks at pixel brightness, and it's tracing pixel brightness over time of this video. And once we give it some dimensions in terms of pixels, so say the distance between A and C, we can calibrate the distance based on the CAD model exactly. And what we do is that once it knows how many pixels each of these points is moving, it can convert that into a distance. And why is this important? Well, we can kind of see that point A isn't really moving very much as one might expect. However, it is the elements of this minute. The interesting thing is there's no minute on the chair, and then the chair lost a little bit when you step back again when it turns control. We can see also the chair turns exactly where it came from. There's no fermentation, which however we know that these types do break. Okay, so this perfect environment with fatigue and because we know that looking is low, not really enough to understand the fear of them. We can just displacements, but effectively it's totally like what's in it. Not as particular to as I've had these in the past. So then we used Ansys Discovery AIM 2020 to a simplified version of the actual physical experiment. So because I installed this on my computer, I actually ran out of RAM to mesh and analyze the entire chair. So what I did is I just split the load case in half and only load one leg of chair, just for simplicity, because I don't have access to the computing power that we have at school just because of COVID. So on my laptop, this made the most amount of sense. And for discussion purposes, at least it gives us some idea of what's happening. So I applied half of the load to the top of the arm here, and we can constrain the bottom with a contact condition or just a fixed constraint, depending on how in detail the students want to model it. And then at the peak of this load case, we're measuring a displacement of approximately 4 centimeters in the location of this point C here that we were concerned with. And if we look at the stresses in the actual leg of the chair, we can see that these are just von Mises stresses that we're looking at. So anything that's in red is a high level of stress, and the peak stress is actually in 23 megapascal. We can take a cross section of this part of the chair, and we can see that it's actually red on both the top and bottom surface of that leg. And the reason for that is it's in bending, as one might expect. So the bottom would be in compression, the top here would be in tension. So that would make sense that if you continually sit on the chair, most likely it's going to break in this location here. And I intentionally did invest a lot of time in getting this to correlate. This was literally the first analysis model that we set up. Maybe in a 30 minutes to an hour, I was able to do this, and we picked off the highest amount of stress was in this location here, which coincidentally is actually fairly close to where that initial failure that I showed in the first slide came from. So that's encouraging to see. However, we haven't closed the loop and continued to refine and correlate this model because this is just for discussion purposes.
And actually, what was your peak displacement when you did the sort of rough experiment too? Just
great question. So now overlaying the animation from the Ansys model to the video, and they're both scaled accordingly. you can see it might be slightly out of phase in terms of timing, but the peak displacement that we were measuring was about 5 centimeters, and we were getting 4 in the simulation. Okay, I literally Googled the Young's modulus and material properties of bamboo, and there was a variability of like an order of magnitude of things, depending on I just nominal properties. So we're pretty close. Just to might even have students perform a simple experiment to actually calculate Young's of the middle because it could be reinforced cell at the surface within that's already eaten off. Could put a retaliate in the flight, which would help difference. But as of now, I really looked at in detail. But using non-properties for bamboo, how we get, and it's in the 5 centimeters versus fairly close. But here, the location C should be in location A, and how they're kind of move back one slide again. Hopefully, that makes a little bit of sense. Yeah, and with that, I get the state of what obviously this is really one stat and time step, so the entire frame to get the students with. An interesting idea is to leverage kind of a lot of us are working from home now. It's a lot easier that we're able to get types of based on other, and conducting these types of experiments are a little bit difficult. So just in my kitchen actually. Other than that, hopefully we can some input from that's kind of where we're at right now and how we depends kind of one's input on what steps of this process are running up to and steps of this process using artificial intelligence. We show example of what's occurring, but with all the details of that particular process. With that, I'd like to stop talking and open the floor up to any questions. I will jump back to this slide just while we're asking questions because it probably is the one that everyone wants to know about. This one here.
I just wanted to say one thing. This is a very large project. So what we are thinking of is different programs will focus on different aspects of the project. It does not need to be done in by one cohort. Say if there are 2B, 2A, 2B, 3A, and 1B here, for example, in fall, in say winter, then what we do is we get 1Bs to do something, 2Bs to do something else, 3A to do something else, and in the end come together to see the holistic picture. And there are portions of this which will just be aimed for a postgraduate course. So the students get a complete picture, but they get to partake and get their feet wet or hands, fingers wet, whatever, in some aspect of the whole thing. So
The
now,
way
Yeah.
the way that I
Andrew,
envision that, sure, go ahead.
I was going to ask if you can go back to the slide with the numbered steps.
Sure.
What do you see as the merit in validating the FEM at step 4, it seems as though there's another validation or correlation step at step 8.
Great question. That really is, I wouldn't say it's a redundant step. It's more for segregation of what Sanjeev just alluded to. That I really, or I think we envision collectively that steps 1 through, let's say, 4 are going to be handled by a lower year engineering student, and they're going to collect the reverse engineering load case data. They might enable or have a digital twin of that, okay, where they have an analysis model. They might not understand everything that's going into the analysis model, but effectively they're only going to correlate and validate the static stresses or the static strains in a static load case, okay? And then when you go to the upper year course, what we're actually going to do is a fatigue test, which incorporates a totally different thing. And instead of just correlating the stresses and strains, what we're going to be correlating is the failure location, the failure mode, and the cycle counts to failure, effectively the life. So that's a totally separate thing that is probably more targeted towards an upper year student or a graduate level environment. So the first validation is only for the static load case, which is step 4. The correlation in step 8 incorporates that step 4 validation because that's an input for the fatigue engine. But step 8 will actually be correlating the not only the mode shape of the fatigue failure and what load case is most damaging, but the cycle count to failure. Hopefully that answers your question a little bit.
Can we go back to the previous slide then?
Sure.
Please? It helps. It helps. On that previous slide, it sounds like so this this iterative building up the digital twin in the finite element model. I had understood from before that there would be you'd place these chairs in arbitrary places and whatever happened to them. How do you envision being able? What I would imagine there is maybe you could put some strain gauges on there and record the strains, but actually knowing what caused those strains, what the actual inputs were, how would you go about that? Because I think that would be very important to calibrate the digital twin.
Excellent question. So I don't know if you can see here under step 2, the usage data, we're going to implement a variety of different sensors, a gyroscope or an accelerometer we're going to place in critical locations. We'll have a stereo camera system that will actually be pointed at the chairs themselves so that we can actually measure displacements using that optical technique that I described a little bit later. We're going to affix microphones, a stereo microphone system, so that we can use an audio technique, and then we're going to embed strain sensors on the surfaces. So from that sensor fusion perspective, where we have all of those variety of data streams that we can then kind of correspond, okay, this combination of sensor data corresponds to a 70 kilogram male sitting on the chair. And we can obviously look at the video to validate that. But in terms of the center of gravity of the loading and the intensity of the loading, that we're not going to be. We could put maybe even a load cell underneath the platform that the chair is sitting on. That might be a good idea. But this is really where the project's still in the development phase on that front. So it's a great question that you asked. And
Steve,
Like
you're talking about the inverse where we know the displacement and we have to figure out the loading that causes the displacement. I think that part we have not emphasized in this particular setup. That will be between number 4 and 5 stage, but it'll have to be done because it's a chair. I think we could do it very simply. If it was a bike frame, for example, then the problem will, it will require modal analysis and stuff like that. So
yeah.
that bit we may need to add as required.
Okay, I may be showing my ignorance here, but
No,
I
no, no,
mean,
not at all.
what I'd be thinking is that, and I think you highlighted it, was you need material properties
Yes.
to get what's happening with the chair, and there's a stress strain relationship that gives us the material properties. Wouldn't we need to know what the load was in order to get some sort of relationship to back out what what the Young's modulus is? Like we from all the instrumentation you highlighted, you can get the strains,
Yep.
but you still don't know what the load is.
We might have to put a butt measure, something right on the butt
Oh,
level.
good. Yeah. Okay. That's the piece that to me, and Andrew alluded to that, and that to me was the piece that I was kind of missing.
Yeah.
Like, in situations that we've gone through, it's actually the step 6 or whatever it was where you had a really well defined test apparatus which
Right.
showed, I'm applying this load and this is the resulting strain.
Right.
That's the kind of correlation data, yeah, the test apparatus. That's the kind of correlation that is often needed to back out,
Yeah.
the material properties that really are probably in play.
So in all of this, right? When like this is at the moment we are just testing out our system. Like it's a pre-implementation phase, just to figure out a few things. When we actually implement it, right? We will do we will get our co-op students to go through the entire process with very little help from us, and we are especially watching where they stumble. And wherever they stumble, it's our we have to figure out, hey, why did they stumble? And because if they have stumbled, our other students will do so as well. And then we let them go through all the way to the end. And by the time they have done one iteration, majority of the issues are known, highlighted, and sorted out. And so by the time we reach the classroom, I think we do a small scaling up first, then we do a larger scaling up. So between the testing with the co-ops, the small scale up, most of the issues are tackled. When it goes to the students, I think other than kind of inundating sometimes or basically misplacing something or doing some silly mistakes, I think the problem is usually quite doable.
And
But
I
we
think with
want to
some of
need
this,
some
we can do some experimentation in advance of handing it over to the students to figure out some of this stuff. Sanjeev mentioned the bridge that civil engineering students build. They're building that out of like rigid house insulation foam, the 2-inch thick sort of Dow Corning whatever foam, and so we had to experimentally figure out what are the properties of this foam, so you can give those numbers to students for their analysis. And we may have to destroy one of these chairs in advance, which I think my co-op students would probably enjoy doing, or seeing anyway, to
all
figure
students
out what
like.
those properties are. Yeah.
I think all students want to destroy a chair.
Yeah.
We have to keep them safe somehow. That will be the tough part. But so the key idea is that this is uh, this is our first foray into designing a complete machine. Uh, and I'm quite scared because it needs a little bit of confidence to sort of deal with one or two cohorts all at the same time, yeah, all encountering different problems, and yet successfully take them through the whole design process. Um, Once we have done that, I'm hoping that we will open the doors for some other areas too. Uh, I have no idea what would be the product. I didn't know that we could design a chair testing machine maybe a year or a year and a half ago. So I'm hoping that by this time next year, I will also know how to address perhaps a very simple, say, fluid mechanics problem or a thermodynamics problem. And I would like to go in that direction, and I also would like to basically have a electrical, some. But what those problems are, I think they will tell me themselves by the time we have implemented the first mechanical thing completely. We will know the scope, and I will look for some parallels in those domains, and we will be able to find it. Uh, Now, in this particular project, right, we kind of kicked off just to give a essence, but I would like industry to be involved in the development and scoping of the next problem. Whenever industry is involved, the industry always tells you of a project which, if from a perspective of a classroom, is this large. And we have only time for this much. So between this large and between this much, together, we want to come and hone on to something which is about this big, right? Which is not real classroom, which is not real world, something in between. In order to do this, we need involvement from you. And we are basically calling this engineer in residence. So this is where the connection between industry and academia begins. And this is the industry side of things. Then once we have developed this activity together, most of the piloting will be done by co-ops, which basically means first year co-ops doing under supervision were able to solve it. It means upper year students with a little bit of supervision will be able to solve it. So we are making that little extension, and we want some variability. If mechatronics uses it, perhaps we are heavy on the front end. If mechanical uses it, we are perhaps heavy on the back end. If electrical uses it, we are basically perhaps heavy on data filtering or some of the AI version, which Andrew talked about. So things like that. So different programs will focus on different things, and we are going to reuse the equipment and the two software tools for a number of cohorts. So we have the students get exposure to the appropriate tools at the appropriate places. Furthermore, in all of this, we are developing different layers of expertise and exposure. The first and the bottom layer is any student who has done this activity. The layer above it is the co-op students who helped us build it. The layer above it is co-op students who have basically gone and worked in industry. So this pyramidal structure that we have developed, we might even be able to convince the engineers in residence to bring some projects in this domain and do it here at the university. So this is like reverse co-op. In co-op, the students go out to industry. In this case, we are getting industry to send some small, simple problems here to the university and use resources here to solve it. In the coming days, when co-op jobs are going to be scarce and there's going to be very aggressive sort of seeking of co-op jobs, this might be an alternate to address the need for very large number of co-op jobs in a 2,000 student intake program. That's what we have here at Waterloo. So there are many, many facets. So this particular domain, I want to call it the Ansys design analytics domain. And this is an example of what I want to do in it. And hopefully in a uh, span of attempts, we want to make 2, 3, 4, 5 such experiments, which could basically bring real world exposure to our students.
Yeah, thanks. And then I've got the sort of the document you guys sent a couple of days ago, and starting to go through that. Done made a first pass. I've actually got a specific question though, or something I'd like to understand a bit more on what we've got in front of here, and this is on step 9.
Sure.
Because what we've got to this point is a well-validated correlated system and approach to generating first time through on a design. When you talk about accelerated design at step 9, what sort of activities do you see taking place there?
Okay, that's an excellent question. So a lot of the benefit, in my opinion, to using a digital twin approach or analysis techniques in general is that the prototyping phase is accelerated for product development because you can effectively cross off a lot of potential options off the list simply through analysis alone because you might not have a 100% accurate in an absolute sense result, but the model that you've generated gives you directionally enough confidence that you can say options A, B, and C are okay, but all of the rest are not worth investigating from a physical prototype perspective. So that's really what the language of accelerated design means. And then also it gives you a step up or a more a leg up on adapting this technique to a totally different machine. So it could be a component to some consumer electronics device, or it could be a bridge, or it could be an internal combustion engine. This is kind of just an archetype for product design in general. Hopefully that answered your question a little bit.
Yeah. Overall, yeah, exactly. Yeah. So basically, the idea is perhaps doing some sort of redesign of the of the starting point, but then virtually validated. Go through a couple of different options.
Yes.
Give them a target of reducing the weight by 20%. Now, what do you do?
Yes.
And then go from there. So, and I think, to be perfectly honest, that's where from an industry use of simulation standpoint, where
That's the benefit.
a lot key here.
I think that's the when we do redesign, and or modifying the existing design, that is where the great benefit is. I totally agree with that. So we want to build this design analytics hub. It will have links to other hubs as well, like the autonomous vehicle one. But that's the big aim or the goal in the coming years. Uh, to to achieve this, to leverage industry involvement, I want to sort of participate in a uh, NSERC Alliance grant. Right now, NSERC Alliance is typically for research projects, but in this case, the research will be more on a holistic, closing of the loop type of system, as opposed to in a particular aspect of analysis, right? So we will, so we'll have to work together to kind of to build that. But anyway, that's a little bit in the future. Um, but we would like to do some leveraging if at all possible.
Steve, I don't know if they've provided anything yet, but what is the shortest term ask here?
Basically, there's a proposal on the table for an Ansys sponsored design hub as part, around this idea, as part of the Ideas Clinic. Um, I'm taking a first pass through right now, collecting a couple of questions, and then we'll start socializing it and talking to key folks like Dipankar and Martin, how we move forward.
I basically like to ensure that since this is an academic size, right? If, for example, we want to do it remotely for some other schools, it would be possible to do so.
Mhm.
Right? And I think that's basically one of the advantages. But I think what we are attempting to is, in my opinion, uh, quite uh, quite advanced and quite world leading as far as engineering education is concerned. And that's the kind of thing we really want to be part of.
Well, I think it's. Sorry, I'm just going to turn my camera off because sometimes I have bandwidth problems. So yeah, I did want to say I think this has got a lot of key aspects. Not just simulation, but the entire all the challenges of instrumentation, data collection. Really is a completely holistic. Will give the students a holistic understanding of what's involved in product development and product design. And then particularly ending with the sort of virtual validation of design alternatives, given that baseline, I think it was a nice complete story.
Yeah, and if the engineer in residence aspect works as well, right? The students, when they interact with people with industrial experience, the conversation may not just stay on the chair. It may wander a little bit here and there, but that wandering is very crucial, because I think it that is what attracts the students to work in this domain. So it would be very good if we can move forward. Uh, so I think we just wanted to, this meeting was just to share with you what we have got. Is this entire process foolproof or complete? No, it is not. It is a work in progress. And we would like you to partner with us anyway. It doesn't really matter. And I think as we go forward, I would like to invite you to partake with us maybe into bi-weekly meetings, just to see where we currently are and where we are headed, and give your opinions on it. And let's start building this project a little more close to how it would be done in industry, but for use in an academic environment.
Actually, just on a practical standpoint, do you see progress given the current situation and doing experiments
Oh,
in your kitchen, or is this
yeah.
a great idea here, or does the next step really rely on us getting back?
Oh, no. It doesn't rely on. I think we are. You guys. I know you guys are going to do your best. So we would like you at the table, regardless. Okay. The idea of facilitating us is a separate thing, but we would like to work with you anyway. All right. That's not the question. As far as us going back to the labs is concerned, labs are beginning to open as we speak, but Steve, but Chris and I have decided that we are not going to rush into the labs. So we will put in our request to go back or send a few students to the lab, maybe in the third week of this month or maybe end of this month. And that will only be 2 or 3 students, and we have a very large space, so the social distancing aspect won't be an issue. But if this project needs some lab equipment and lab space, then we will have access to the facilities to build it.
Yeah, and I was not suggesting trying to go back early by any stretch. I was just kind of
No, no,
wondering
no, no,
how.
no, we are not.
Yeah,
No, I know. Anybody who has kids
yeah,
can and appreciate it and understand it at this level, right? So that's not the intent. I'm just giving you that's our
yeah,
approach as we speak.
yeah. Okay.
You
So
asked, sorry, you asked earlier about AI, and I mean, given the amount of data that exists here, I think there is opportunity to integrate AI into it too.
I love it. I love it because the newer domains attract the students quite a bit, and uh, as we basically go into it, it'll be good. So I want to keep my eyes open for it, and I want to keep the opportunities open for that. That's basically the goal.
It also, gives us an opportunity to hit programs we might miss otherwise. This is a very sort of physical mechatronicsy sort of activity in a lot of ways. But if you can start getting into big data, running experiments, the structural side, you can hit civil, you can hit management engineering, software engineering, and all of a sudden this one activity now, we don't have to build 14 different activities for our 14 programs because that'll kill us.
Yeah, that will definitely kill us. Let me ask you, gentlemen, another question, but this is related to my research. All right. So the other day, one of my master's students graduated, and I had a reader. The reader mentioned that they were using fine, right? Um, this totally blew me out. And he said, "Why don't we use it for toolpath planning and machining?" So I had no answer for them. I didn't for them. But my question to you is, how do they model surfaces using convolutional neural networks? Is there any link? Is there any idea? Is there any papers or whatever reading?
Hmm.
Anyway,
You know,
keep your
the
go ahead.
one thing I'm thinking of is level set methods for geometry representation,
Uh-huh.
um, which is kind of representing analytic surfaces in a voxel, smooth analytic surfaces in a highly voxelized environment. Basically, it's
Okay.
just isosurfaces of a distance field is the simple way of thinking about it.
Okay.
But generating the distance field, has a number of different techniques, and I think that could be one of them.
All right.
But yeah, interesting.
I even arranged for him to have a 1 hour conversation
Yeah,
with me just about it. But I think he got busy that day, so I have to remind him again that hey, I need to know a little more about neural networks and how they model surfaces.
yeah,
So if I find out more, I will raise that issue in this forum. It kind of it's a mutual learning process that I am in. Anyway, I think this was an information session, and I think we are inadvertently forming the Design Analytics Hub. You guys are part of it, whether you like it or not. Um, uh, and we will keep moving forward. All right, and that's basically uh, that would be a good way to move ahead. And Andrew, as we go forward, right, we will every bi-weekly we will arrange a meeting just to make sure we are headed in the right direction.
Sounds excellent to
Sounds
me.
excellent.
yeah.
Thank you,
Thanks very
guys.
much.
I
Definitely
think
appreciate it. It's really good to see the overview of this. It kind of brings it to life.
yeah, and it's very easy to thank you guys because all I have to say is thanks, Steve's.
Yeah, Steve.
Yeah.
All right, guys.
Thank
You have a
you.
great evening, and keep safe.
Yeah.
Yeah, you too.
Thanks.
All
Talk
right.
to you later.
Thanks.
Bye bye. Bye
Bye.
bye, guys.